In the last video in this section, we're going to utilize dot product, cross product, and magnitude to be able to find, and the equations of planes and lines, to be able to find our distances between different types of points and geometric objects in space. So, three different formulas, one of which is if you have a plane and you have a point in space, you can find the distance between that point and plane by finding the projection. And the projection, remember, is just taking a vector and laying it on top of another vector, essentially. So let's say we have this point Q and we have a normal vector. All we're going to do is we're just going to take and we're going to project a new vector, which we're going to call PQ, and we're going to project that onto the plane to be able to find the distance between the point and the plane. And to be able to do that, we're going to find the absolute value of magnitude PQ dot n, where n is a normal plane and PQ is a vector from the point on the plane, or any point on the plane, to the point that we're interested in, divided by the magnitude of that normal vector. A second formula we can look at is the distance between two parallel planes. And essentially, if we have an equation or two equations of planes, we can find a normal vector to one plane and a point on another plane. And essentially, we do the exact same thing as what we did before, and we're going to find the dot product. All right, so if you look at our formula in the numerator, this almost looks like the equation of a plane. All right, it's the dot product, and then the d is equal to whatever that constant is. And then that's the magnitude in the denominator of the coefficients of the other plane. All right, so we're just basically, again, trying to find a projection by utilizing a dot product and a magnitude. And then to be able to find the distance between a point and a line in space. It's a little bit different because we don't have a normal vector. But what we can do is we can find a normal vector by finding the cross product. So that's why we use the cross product in this one instead of a dot product, is because we don't have a normal vector to be able to help us find the projection. Right? So the projection helps us to be able to find that distance. So we have a point Q and we have a point P that falls on the line. So once again, we just find the projection of PQ onto the line. This time we're finding the cross product, dividing it by the magnitude of U, and U is going to be a direction vector. All right, so that's a basic overview of how these formulas are derived theoretically. Now, let's put these into practice. So we're going to look at an example of each type. So we have a distance between a point and a plane first. Let's call this point that we're given Q. The plane that we're looking at is 4, 6, 10. So we know right away that a normal vector to that plane is 4, 6, 10, because that's the coefficients. All right, so remember that trick is that if you ever need a normal plane or normal vector to a plane, you just take the coefficients right away. We need a point P on the plane, and here's an easy way to find a point on the plane. Just define y and z to be 0. In other words, we're finding an intercept. So just like you did in pre-calculus, it's pretty easy to find an intercept there. So if 6y, or 6 times 0, and then 10z is 6 times 0, then we get 4x, which is equal to 12, or x is equal to 3. All right, so we get the point 3, 0, 0, and then the vector PQ is going to be equal to 3 minus 2, which is 1, 0 minus 3, which is negative 3, 0 minus 4, which is negative 4. And at this point, now we can use our formula. All right. Remember, our formula is going to be, to find our distance, it's the absolute value of vector PQ dot vector n, and we're going to divide that by magnitude n. And so that's pretty easy to find. PQ is going to be 1 times 4. I'm sorry, PQ dot n is going to be 1 times 4 minus 3 times 6 minus 4 times 10. And then the magnitude of n is going to be 4 square plus 6 square plus 10 square. A couple ways to write this solution. In the numerator, we have 4 minus 18, which is negative 14. Negative 14 minus 40 is going to be negative 54. In the denominator, That's going to be the square root of 16 and 56, or sorry, 52, I think. So that would be 16 and 36 and 10. I think that's going to be 152. I'm going to check in the calculator just to verify that. Yep. And I do believe that 152 is divisible by 4. And so we can write that as 54 over 2 roots of 38, or finally 27 out of root, or divided by root 38. And that's our distance in whatever units we have. Second example, distance between two planes. And of course, the first thing we wish to do is we wish to determine if the planes are indeed parallel. Right? So if they are parallel, let's define P1 to be equal to negative 3x plus 6y plus 7z, which is equal to 1. And let's define P2 to be the plane 6x minus 12y minus 14z is equal to 25. And I want you to notice that each of the coefficients of P1, if that was multiplied by negative 2, then that would equal the coefficients of plane 2, which means that the normal vectors are going to be parallel to one another, which means that the planes are parallel. All right, so we're going to say, since negative 2p1 is going to be equal to p2, except for the coefficients, which we don't really care about. That's like our intercepts. In fact, if we wanted to, we could just say if negative 2n1, meaning that's the normal vector, is equal to n2, they are parallel. All right, so, and of course, if they're not parallel, then the distance would be 0. We're going to use that trick again, where we just let y and z be 0. So if those two are 0, then 25/6 is going to be a point on the line. And so finally, we have that plane 1 can be represented by negative 3x plus 6y plus 7z minus 1, which is equal to 0. And finally, we get that a is negative 3, b is 6, c is 7, d is negative 1, and then x naught is going to be 25/6, which is the first point, and then y naught and z naught are both 0. And now we're just going to throw all of those back into our formula. All right, so the distance d, remember we take a dot product, and then we're going to add this other d coefficient, so that's going to be negative 3 times 25/6 plus 6 times 0 plus 7 times 0 minus 1, absolute value. And then we're going to divide that by the square root of a squared plus b squared plus c squared. And in the numerator, I think that winds up being 27 halves, because it looks like we have negative 25 halves minus 1, which is negative 27 halves. And then the denominator, we have 9 plus 36 plus 49. That's going to be root 94. All right. And I don't think 94 has anything that we can do to make it any more simple. So we can write this as 27 over 2 roots of 94 for our final answer. One last example. This time we have a point in the line. All right? So let's call the point Q, and we certainly need a point P. Now a point on the line is really easy to get. We can just let t equal 0. If t equals 0, then we get the point 5, 0, 1. And let's say we need a vector that falls somewhere on that line. All right? So a vector with the direction that we need, the direction numbers, and I think we called it u in the formula. U is going to be a vector on the line is going to be equal to the direction numbers, which in this case is -2, 4, and 1. Now vector PQ is going to be defined as 5 minus a minus 2, which is 7, 0 minus a minus 5, which is 5, 1 minus 7, which is -6. We could throw it into our projection formula. Okay, so the distance, remember, is going to be the magnitude of PQ cross U divided by magnitude of U. Right? So we just need to find a cross product, the magnitude, and the magnitude of, magnitude of the cross product, and then the magnitude of the direction vector, and we are good. Right? So PQ cross U is going to be equal to IJK. PQ was 7, 5, -6, and U was -2, 4, 1. And so if we find our cross product for this, we get 5 minus 24, so that's going to be 29i. We're going to get 7 minus 12, which I think is going to turn into positive 5i. So we get 7 minus a minus, I think there's 4 minuses going on here. So hold on one sec just to make sure. So 7 times 1 is 7, -2 times -6, and we're going to subtract that. So 7 minus 12 is -5, and then we have the minus there. Okay, and then finally for K we have 5 minus, for K we have 28 minus 10, which is 38, and that's going to be a J, and this is going to be a K. Alright, and then mercifully we can find the magnitude of this. Alright, so for our magnitude, so this is magnitude PQ cross U, that's going to be equal to root 29 square plus 5 square plus 38 square. So 29 square plus 5 square plus 38 square is going to be 2310. Magnitude of U, thankfully a little bit easier, square root of -2 square plus 4 square plus 1 square, that should be root 21. And our distance D is going to be equal to root 2310, or 2310 over root 21. Let's see if they're divisible. They are exactly divisible into 110, and I don't know if there's a perfect square in there anywhere. So I know 25 doesn't work, 49 doesn't work. We could just leave it like that, unless 110 is divisible by 4, which is not. Alright, so we'll just leave it like that. Sorry, I'm sitting here with my calculator trying to figure out a perfect square. I don't think it's going to work out, but that's pretty cool that it does work out fairly nicely for us. So hopefully this gives you a few good examples as to how to be able to find the distances between surfaces in space and any given point in space.